In section 3.5, we're working on identifying asymptotes of rational functions, and we have example 2. We have a graph of a function f of x, and we want to identify all of the asymptotes, and we also want to state the domain of the function. You might take a moment and pause the video and try to do this problem for yourself, and then we'll go over it together. Let's talk about the vertical asymptotes first. We can see the vertical asymptotes in the graph where we have vertical dashed lines at x equals -4 and also at x equals +4. There are two vertical asymptotes, x equals -4 and x equals +4. And we can identify them from the dashed line, but we should also understand the behavior of the graph that's causing the vertical asymptote. So in particular, let's look near x equals -4. Let's look just to the left of x equals -4. As x approaches -4 from the left, y values are getting larger and larger, following this arrow up to +infinity. Let's write that down. As x is approaching -4, the y values, the function values, f of x is approaching +infinity on the left side of -4, and on the right side of -4, the y values are going down to -infinity. So that's exactly the definition for a vertical asymptote. And we have the same behavior, same type of behavior at +4. As x approaches +4 from the left side or the right side, the function values are shooting up to +infinity or down to -infinity. Okay, let's go ahead and find the horizontal asymptote. Horizontal asymptote is represented by the horizontal dashed line. So we can see its equation is y equals 1, and we have our answer. And we should understand the reason for the horizontal asymptote is the behavior of the graph, is the behavior of the function. And specifically, now we're looking at the end behavior. As x approaches positive or -infinity, what are the function values doing? Out here at the right end of the graph, as x gets larger and larger, the y values are leveling off. They're getting closer and closer to 1. And we see the same behavior at the left end of the graph as if we follow this arrow, as x approaches -infinity, y values are also approaching 1. Okay, so we have our asymptotes. We should go ahead and state the domain. Maybe I can fit it here on the other side of the screen. The domain is all real numbers except for, can you see which numbers are excluded from the domain? There's no function value at -4 or +4 at the vertical asymptotes. Right? The rational function is always undefined at the vertical asymptote. So -4 and +4 are not in the domain. And then if we want to write that in interval notation, we need to start from -infinity and go up to -4. And then we need to continue on the other side of -4. We need to go up to 4. And then we need to omit 4 as well. And then continue on to +infinity. So in interval notation, this is our answer. Okay, so we know how to find the asymptotes from a graph, and now we want to find the asymptotes from a formula. So you can see example 3 here. You can see an algebraic representation of several functions. We want to go through and find their vertical asymptotes first, and then their horizontal asymptotes a little later. How do you find vertical asymptotes? It's really a two-step process. First, we want to make sure that the function is in lowest terms. If it's not, we want to simplify it. And then all we want to do is set the denominator equal to 0 and solve for x. Okay, so let's give that a shot. In example 3a, we have x minus 2 over x squared minus 9. This is in lowest terms, but maybe it's a good habit to factor anyway. If we're able to factor the denominator, then let's just go ahead and do it. And we see that there is no common factor in the numerator and denominator. So that means there's no factor to cancel. That means we're in lowest terms. And so then we just want to go ahead and take the denominator and set it equal to 0. Doesn't matter if we take the factored form or if we take the original form in the problem. We'll get the same answer. If x plus 3 equals 0, that gives us x equals negative 3. And if x minus 3 equals 0, that gives us x equals 3. Two vertical asymptotes. Okay, let's do this a couple more times. So this time the numerator can factor. There's a common factor of 2 in each term in the numerator. It's not necessary to factor it out, but it's fine if we do. When we see the factored form, we see there is no common factor in the numerator and denominator, and so we go ahead and set the denominator equal to 0 and solve for x. X equals negative 1. And then one more time, we can factor the numerator if we like. There's no common factor in the numerator and denominator, so the function is already in lowest terms. We can take the denominator and set it equal to 0, and our vertical asymptote is the line x equals 1. Okay, so we found vertical asymptotes for these functions. Let's go ahead and find horizontal asymptotes for the same functions. So here is a definition of a horizontal asymptote that you've seen before. And then if you want to find horizontal asymptotes, then there are 3 cases to consider. And you might pause the video and read through it yourself. I'll try to summarize the main points as we work through the examples. The thing that we need to notice is that we're looking at the degree of the numerator and the degree of the denominator every time. So that's where we start. Degree of the numerator, degree of the denominator. Degree of the numerator, degree of the denominator. So let's go on and check the degree of numerator and denominator in this first example, and then we'll see which case we have. Okay, what's the degree of the numerator? I bet you said 1. The degree, you know, is the highest power on the variable x. In the numerator, degree 1. In the denominator, degree 2. And so that means that we have a horizontal asymptote. Well, let's back up for just a moment. So notice the degree of the numerator is less than the degree of the denominator. So we're in case 1. If the degree of the numerator is less than the degree of the denominator, there's a horizontal asymptote at y equals 0. Horizontal asymptote at y equals 0. Okay, and then let's do the next example. This time, the degree of the numerator is 1, and the degree of the denominator is also 1. So I believe that's case number 2. If the degree of the numerator is equal to the degree of the denominator, then we have a horizontal asymptote, and it's determined by the leading coefficients in the numerator and denominator. So more good vocabulary. What's the leading coefficient in the numerator? It's the coefficient on the highest power of x. So here's x to the first. The coefficient is 4. So we have a horizontal asymptote whose numerator is 4, and denominator is the coefficient on this x. It's 1. It's 4 over 1, or just 4. So let's write horizontal asymptote at y equals 4. Okay, one more example. This time the degree of the numerator is 2, and the degree of the denominator is 1. And so let's see which case that is. So that's case 3. If the degree of the numerator is not only larger than the degree of the denominator, but exactly one more. Exactly one more. So denominator had degree 1, numerator 1 more than that, had degree 2. Then what we actually have is an oblique asymptote, or sometimes it's called a slant asymptote. And we can get the equation of the slant asymptote by using synthetic division. So let's go ahead and try that. So there is no horizontal asymptote. We could box that up, but there is an oblique asymptote. And the way we're going to get it is with synthetic division. So we're going to put the coefficients of the numerator inside. We're going to put 1 for x squared, and 1 is the coefficient on x. And don't forget the constant at the end. We have to have a plus 0 to finish the synthetic division. Out in front, we have the opposite of this constant, -1. So we have a positive 1 out in front, and then we can do the synthetic division. 1, that's a 1 right there, and then a 2, and then a 2, and then a 2. And so what does this tell us? This tells us that h of x can be rewritten in the following form. So let's see here. A good review from section 3.2. There's the quotient represented by those two numbers, and the remainder represented by the last number. And we can write the function as the quotient 1 times x plus the constant 2 plus the remainder over the divisor. Okay, so now that we've rewritten h of x, let's go back and see how that's going to help us. In case number 3, we did the synthetic division. To get the equation of the oblique asymptote, we divide and disregard the remainder. The equation of the asymptote is just y equals the quotient. Y equals the quotient. And so the quotient is just x plus 2. And so the oblique asymptote is at y equals x plus 2. We haven't seen the graph of an oblique asymptote yet, but we will before the end of this section. In fact, what we want to do now is we want to go ahead and take each of these three functions we've been working with, and we want to sketch a graph. And so that's what we'll do in the videos to come.